Now see, in this problem we have to find area bounded by this inequality as well as this inequality. And you know, when we plot inequality on a two-dimensional plane, it represents an area on two-dimensional plane. So this inequality will bound some area on two-dimensional plane, as well as this inequality would also bound some area on two-dimensional plane. Now we have to find area common to both the inequalities. So we have to find that region that is present in this inequality, those values of x and y you can say that satisfy this, as well as those values which satisfy this. So basically on graph we see area representing the values that satisfy this and area representing the value that satisfy this, which is common to both. We have to find common solution. It means graphically we have to find common area. Now to plot area bounded by this inequality, first of all we observe that this inequality, whatever area is represented by this inequality, would be symmetrical about both x-axis and y-axis. And this is because you can see, if I replace x by minus x in this inequality, if I replace x by minus x, I change this to minus x, and I change this to minus x. I take minus common, it becomes mod of x plus y, and if I take minus common from the side, it becomes mod of y minus x. So you can see mod of x minus y. So you can see this inequality, this term becomes this term and this term becomes this term. So there is no change. There is no change in this inequality. Similarly, if we replace y by minus y, there's no change in this inequality. So when there is no change in replacing x by minus x and y by minus y, it means region is symmetrical in both the axes. Whatever we have in right half, symmetry of that would be in left half, and whatever we would have above x axis upper half, symmetry of that would be there in lower half. So we decide to do it, plot the graph region of this inequality only in first quadrant, and then we take reflection in both the axes. To plot in first quadrant, you can see we need to make cases here. Because see, when we are plotting in first quadrant, x is greater than 0 and y is greater than 0, and if both are positive, we can remove this mod sign. We can get rid of this mod sign, right? Because this is mod of x plus y, so we can remove this mod sign. It becomes x plus y. But on this side we have to make two cases. We'll have to make two cases because this is mod of x minus y. So to remove this mod, we'll have to make two cases. First case is y greater than x. The second case is y less than x, or x greater than y. When y is greater than x, this mod will return a positive quantity, and positive quantity is y minus x. And this, on simplification, it becomes y less than equal to 4. So when we are plotting y greater than x, we have to plot y less than equals to 4. Same on this side, when y is less than x, on simplification we get x less than equals to 4. Now let's plot this first case. Y is greater than x. This is the region that represents y greater than x. Region above y equal to x line. You know, this is y equal to x line. So this is the area in first quadrant which is above y equal to x line. This area. So in this area we have to plot y less than equals to 4. Suppose this is 4 units. We have to be above this line. We have to plot above this line, region above this line, but region below this line, on and below this line. So this is the area. Similarly, when we take y less than x, means we are below this line in first quadrant, and we have to plot x less than equals to 4. This is x equals to 4 line, and x less than equals to 4 means on left of this. So this is the region. Now you can see in first quadrant, this inequality is representing area of the square. Now if we have, we discussed that it is symmetrical in both the quadrants, so whatever we have plotted in first quadrant will take image of that in other quadrants. First of all about y-axis and then about x-axis. So finally we'll get a bigger square. this length is 4, so the bigger square length is 8 units. Right, now we have to find area bounded by this and this. Right, now let's take this case y. Xy greater than or equals to 2. Xy greater than or equals to 2 means y greater than or equals to 2 by x. We know y equals to 2 by x is a graph like this, odd function, so it is symmetrical about origin. Now when we have to take inequality y greater than inequality, and you can see origin, or we can take a point here 1, 0. 1, 0 does not satisfy this inequality. When we replace y equal to 1, x equal to 1 and y equal to 0, it doesn't satisfy this inequality. So this point doesn't satisfy means region below this curve doesn't satisfy this. So greater sign means outside this, and similarly on this side outside this. Right, now we have to find common area between the two curves. So we'll plot square here, square of, and you can see square in first quadrant is like this, and similarly we have square, extension of square in other quadrants. Now this is in first quadrant, area bounded by square, and this 2 by x curve is this, and symmetrically, this curve is symmetrical about origin, so similar area we would get in third quadrant. So if you have to find total area bounded by two curves, we say double the area of the first quadrant. So we say required area is 2 times area in first quadrant. Area in first quadrant is from first point of intersection, say A, to second point of intersection, that is 4. Upper curve minus lower curve. Upper curve is y equals to 4 line, 4 minus lower curve, that is 2 by x dx. And this point of intersection A we can obtain by solving 2 by x curve with y equal to 4. So it becomes x equals to half. So you can see area bounded, we can calculate this integral and we'll get area bounded by two curves. And this is something which you can do yourself. I hope you could understand this sketching.